Okay, that being said, let's get started. So we are continuing our whirlwind tour of cryptography. Again, if you really like cryptography, you can get 14 weeks of this instead of 2 weeks. I encourage everyone to do that because it's important to know. I have never done it, and I regret having not done it. Someday I may take our cryptography course. The other thing to note is we are introducing, this semester we introduced a new cryptography course of applied cryptography. And the hope is to make it much less of a math course and much more of a computer science course that really looks at how you use all these things in a practical setting. So they're not sort of abstract and interesting for their mathematical properties, but they're actually sort of solving useful problems like how do we actually get an internet to work somewhat reliably. So what we'll be covering today are message authentication codes. So we saw before that we had a problem with using symmetric encryption, that it was very hard to provide integrity, so that if somebody modified the message, it could be difficult to tell it was modified. So that is the goal of a message authentication code. We'll then talk about what if you have a password and you want to encrypt things with your password. So far we talked about having random numbers as keys, but there are cases where you want to use a password to encrypt something instead. And so we'll talk about sort of what are the best practices and how to use passwords to encrypt things. Hopefully last night in the exam you had a little bit of thinking about how you might use passwords to encrypt things, or the challenges. We'll then start talking about sort of the first and most popular asymmetric encryption mechanism, RSA, named after 3 professors at MIT. And, you know, there's a bunch of things we can go into after that. I don't think we'll get through this whole list today. But this is the list of things we could cover. So PKCS number 1 is sort of says, given that we have these primitives of RSA and we have DES or AES, how do we actually use them in practice? And PKCS is an international standard that has a number of different flavors that says, here's how you use the primitives to actually communicate messages in a secure way. So it goes from just being a primitive to being sort of a protocol on best ways to use these primitives. Okay, so we're now going to move into hash functions and message authentication. So we'll first start off with a simple hash function. So the goal of a hash function is that you have some message and you want to produce an output. And the property that you really would like here, well, I guess one thing to think about is from a security perspective, what are the properties that we want? So often we use hash functions for different things. So in building hash tables, what we care about is a nice distribution. That we have n hash buckets. We want to sort of take our input key and spread it evenly across all those buckets. But we don't really care like how predictable it is if you can sort of figure out from which bucket you're in, which input key you use to get there, because it's not a goal. Another thing we use hashes for are things like checksums, where we're trying to detect errors. In this case, our goals are things like, can you detect that a bit was flipped in the transmission somewhere with high probability? Can you detect 2 bits were flipped or 3 bits were flipped? Can you actually figure out where those bits were flipped so you can correct them somehow? So again, the goal is detecting errors. There's no security goal there. So the question is, in a security setting, we have a different set of goals. So any thoughts on what we really care about in a security setting from a hash function? Yes?
Make it hard to guess input that corresponds to a specific output.
Right. So one thing we care about is if we see a hash function, it should be very hard to, A, guess the input that came from that. So it should be hard to run it backwards. It should be, okay, that's one goal. Other possible goals, yes?
What's the word? Both hit the same.
Collision?
Collision, yeah.
Okay, so we worry about hash collision. So a hash collision is when you take 2 messages and they hash to the same thing. And I think what you're getting at is that it should be difficult to find hash collision. So you mentioned it should be hard to reverse it and find the message. Now the fact is that a hash is a fixed length. The input is unlimited length. So that means by definition there have to be multiple inputs that hash to the same output. The same way with a hash function in a hash table, you have lots of inputs that hash to the same hash bucket. We're going to have infinitely many inputs that hash to the same output. And the goal is that it should be very hard to find a collision. So why do we care about finding a collision? Why is that a security relevant property? Yes?
You could find a collision easily, and you could craft an alternative message that you could inject into the screen that generates the same hash and guesses value.
Right, exactly. So if you didn't hear it, the challenge is I send you a message, I put a hash on it to sort of prove that it's the message that I sent, If you can reverse it, you can change the message to mean something different, and you can get your message through instead of my message. And it turns out there's a whole lot of other things you can do because of the way hash functions are used. But generally, it's collisions we worry more about than reversing them. And the reason is that in many, many cases, the text of what you are computing a hash over is public. And so it's not a secret what the input was. The real challenge is more about finding other inputs that have the same hash. This sort of goes over the things that we just went over. Okay, so how we might use this, we've talked a lot about passwords. So one way you might use this is to take a salt, append it with a password, and then compute the hash over it. One thing we will see a lot in the application of hash functions is appending things. Because the nice property is a hash function can take arbitrary long inputs and produce a fixed size output. So if we want to take something and sort of add more randomness to it or mix it up somehow, we can just append strings to it, like master secret, connection secret, session secret. We can append salts to it. We can append counters to it. We can append lots of different things to it to get a new output. So one of the properties of a hash function is we should think about is what happens if you change any bit of the input? What will the resulting output look like? In a good hash function, changing any bit of the input will flip all the output bits with 50% probability. So effectively, if any bit changes in the input, you get a completely different output that is sort of unrecognizable in any way from the original output. So again, our goal here is that given a salt and the hash, you shouldn't be able to recover the password. So this is the case that you brought up of not being able to reverse the hash function. So the question is, how feasible is this? And this depends a lot on your settings. Because it depends, for example, on, in the case of passwords, as we talked about before, how many passwords are there, right? It might be, for example, infeasible to recover an arbitrary message, but if we know their passwords, then we can just try a bunch of likely passwords. The function is only as good as the inputs. If the input isn't very good, then the hash isn't going to sort of do very much for us. Any questions? Great. Okay. So here is sort of how we want to use a hash function. We've seen this diagram before with symmetric encryption. We have sort of blocks that are various functions that we use. So here in message authentication, we want to do more than just create a hash. We want to have a keyed hash that says that you have to have some secret to produce a hash or to verify a hash. So we're going to have some randomness. We feed into our key generation box. Our key generation box will then produce a key that we distribute to both the sender and the receiver. And then we're going to have a tag or a hash function where you pass in the message, and you can also pass in some randomness like the salt or other random values to sort of make the output look more confusing. We're then going to create some tag. When you want to verify this, you have to pass in the message and the tag, and it will tell you, 0, 1, does it pass? And what we mean by correctness is that, if we verify a tag that was correctly generated using the right key, then we should get that the tag matches with high probability. And if anything is different about the key or the message being verified or the tag itself, then it will not match with high probability. And we want unforgeability, so you can't find some other message, M prime, this is collision resistance, that will produce the same tag. Okay, so how do we do this? There's a bunch of different ways. So remember when we talked about looking at block ciphers, we talked about them as sort of pseudo-random functions. Now what a block cipher does is it takes a key of some length k, it takes some input, and produces an output of the same length as the input that's encrypted with the key. So to some extent, what this means is that the output is sort of indistinguishable from just totally random bit strings. So this means that we can actually use any encryption mechanism to generate a MAC if we use it properly. The goal, so this means that if we have, a bunch of different messages that have all been encrypted with a key and some set of random numbers, there's no way to distinguish these apart. That sort of means that they're unpredictable. So this, again, is our goal for sort of a provably secure hash function or provably secure pseudo-random function. So the way we can use this to generate a message authentication code is to basically, use this to encrypt some piece of data, which means that we're going to take a hash and we're going to encrypt it with our secret key, and produce a tag, and then send it to the other side. The other side can decrypt it, and then apply the hash function and verify that it looks the same. So this is really just an encrypted hash in some way, is one way to do this. Right? Because if you think about it, this is the same thing, this is sort of the same property that we want encryption to do. The difference is that with encryption, we have sort of arbitrarily long inputs, or long inputs. Sorry, with encryption, we have sort of fixed size inputs, and encryption, we have a variable size input and a variable size output. Here we have a variable size input and a fixed size output. So the only real trick here is how do we compress the variable size input into a fixed size input that we can encrypt, and that's what a good hash function does for us. So that is one way to do it. However, you don't actually need an encryption mechanism to do this because we can actually rely on our hash functions. We can say our key is a source of randomness to our hash function. So if we just mix the key into the hash function, then we will produce some different output for every different key that is hard to reverse. So here's one possible way you might produce a MAC function. So HMAC is a hash-based message authentication code, which is sort of what is commonly used because they're often faster than using encryption directly. So that's what HMAC stands for. So here is an HMAC that people have tried to use. You take the key, you append the message to it, you hash it, and that produces a tag. So that looks pretty good. When you want to verify this, it's pretty easy. You can take the message, you can prepend the key to it, produce the tag, compare the tags, see if they match. So this looks good and people have tried to do it. The challenge here is, what if I want to append to this message? Can I do so? Right? So, with many different hash functions, if I'm hashing a longer input, I take the hash of some prefix of that, and then I just sort of keep on randomizing it as I get more and more input. So what this means is that if I want to extend it, there's a potential with many hash functions. I can take a hash function over a prefix of some message, and then from that, I can just append more things and update the hash and create a correct hash function. So what this says is there's another property that we need for, so what that means is we can actually find what this gives us the power to do is to sort of predict what is the right message authentication code for a message where we don't have the key, because we can take a prefix. So what we want to do is, given this, we want to be able to compute this. And a lot of times we can sort of say, that we can initialize the internal state of the hash function with this hash here. We can then continue to apply the hash function to the new inputs and get a new output tag. And the output tag will be the same as if we had computed the whole hash at once. Yes?
This mechanism less secure.
Yes, that is why it says attempt at the top. Because you can apply this sort of tag that lets you generate new valid message authentication codes for messages you've never seen before. So that is why the simple approach of putting the key and then the message after it doesn't work. It turns out if you reverse this and you swap the message and the key, you would think this would fix it because you can no longer append a new message, and it does fix this problem. Turns out there are other subtle problems that you get when you apply things this way. So the actual method that people use that is recommended to use is this function that is actually called an HMAC. And what we're going to do is take, we're going to have some sort of random numbers, these pads, input pad and output pad. We're going to take the key and we're going to XOR with the input pad and then append that to M, run it through the hash function once. We then take the key with the output pad, append the hash to that, and run it through the hash function again to actually produce the tag. So what we have done here is we've sort of pre-appended some material. We've then hashed it. We then apply a different hash with a different key at the end of it and use the output of that. And this means that it's very difficult to sort of reverse any of this because there's multiple hash steps in the middle that mix it up more. And because we have a second hash step and we append things onto it, you can't play this trick that we had here of appending data to the message. So, sort of the key from this is that how you take these primitives and actually produce useful mechanisms has a lot of subtlety to it, because you wouldn't think you need something this complicated to be secure. You would think that something simple like this would be secure, and for a whole lot of reasons, it's not as secure as you think. Any questions? Yes?
iPad constants, are they linked or?
So these are, I mean, they should be, basically, whenever you see an XOR operation, you can assume that the things you're XORing are the same length. So these are basically like the initialization vectors that we saw for CBC mode with block ciphers, where there are sort of random information that has to be transmitted with the message so that the receiver can verify it. But they're the same size as the key. Pardon me. Okay, so we now have a couple primitives. We have a block cipher and we have a message authentication code. And the question is, how do we compose these in the most secure way? So there's three different ways people have looked at composing them. It turns out that TLS does it one way, SSH, the secure shell, does it a different way, and IPsec, a protocol for securing IP packets, does it a third way. So one thing you can do, which is shown at the top, is that you encrypt the data. So we have the key, we're going to encrypt it using CBC mode, chain block cipher mode with a block cipher. We produce a ciphertext. We're then going to compute a MAC over the ciphertext with some other key and produce a tag from this. So this is called encrypt then MAC. Because we encrypt it first, then we apply the MAC over the encrypted data. So in this case, somebody looking over the internet, who sees this message can actually see what is the MAC is being computed from. So they have sort of a known ciphertext attack here because they sort of know the input and they know the hash function and they know what the tag is. And so what they would try to do is to sort of figure out what the key is. The second option in the lower right is called MAC then encrypt. And in this case, what we do is we apply the MAC, so we get the tag out. We then take the tag and append it to the message, and then we encrypt the message and the tag together using CBC mode. So here we're computing the HMAC over the unencrypted input. So that's why it's called encrypt and then MAC. And then the final choice is encrypt and MAC, where we take the cleartext input, we apply the MAC to it on the right, and the encryption on the left, and we take both of these and send them. So any guesses on which one is most secure? It doesn't matter. And I will say that looking at this, before I sort of studied it myself, they all look equally secure to me. And it is true that in general, they are all relatively secure. The problem comes when you actually have specific encryption mechanisms that have known weaknesses, that some of these are more secure than others. So there's certain cases where some of these fall down. If your encryption mechanism isn't as good, some are less secure. If your encryption mechanism is very good and your hash is very good and has no weaknesses, then they're all pretty similar. But in general, the current recommendation is to encrypt and then MAC. And the reasons are fairly subtle. I can refer to you to the 20-page paper of why this happens, if you're interested. But this is sort of the thing you should take away. Again, the other thing you should take away is that the answer is not at all obvious. And so this is a good reason to sort of, when you're trying to design a secure system, to sort of look what other people have to say instead of reasoning about it yourself. Because with the level of knowledge that we have in this room, or that I have, and that many of you have, there's no way to distinguish which of these is most secure. Because they all seem to have very similar security properties. Yes? So it's not that it's vulnerable, it's that that is the kind of attack you have. Because you know exactly what's being hashed. In the second case, when you see the hash has been encrypted, and you don't know what you see is just, you're seeing just the ciphertext of the hash, and the hash is over something you haven't seen before. So you have to sort of reverse the encryption before you can try to attack the MAC function. In the first case, you can try to attack the MAC function directly because you can see all the inputs of the MAC function are public. So it's not that it's vulnerable, it's just describing what kind of attack scenario you have. Other questions? Okay, so this is what is actually used in TLS. So TLS has a payload. So what it will do is it'll take the payload you want to send. It'll attach some other data, sort of a compression method. It will then apply the MAC and provide over the payload. There's extra padding that you add that is just random information. This is not part of the MAC. And it turns out that if you add random information to your MAC, there's some risky things that go on there that I don't understand. But then all of this is encrypted and sent as the ciphertext. So the padding does things like round it out to a multiple of 128 bits so that it's the right size for a block cipher. You can also use padding, for example, if you don't want people to know how long your message is, you can expand short messages to be longer at this point. But the MAC is really just over the payload data you want to send. So this is just really an example of how this is used in practice. And for TLS, there's a number of different options. So the MAC that it supports, MD5, SHA-1, SHA-256. The encryption mechanisms are really AES or 3DES, or this thing called RC4. So in addition to this, there are also mechanisms, sort of modes of operation of block ciphers that incorporate message authentication into the mode of operation. So here we saw that you had to sort of create a MAC separately from the encryption stage. With these different modes, you can basically incorporate the MAC into the encryption itself, so you don't have a separate stage. And so these are really sort of different mechanisms on how to use things that provide sort of what's called authenticated encryption, because we are both encrypting and making sure the message is authentic at the same time. So what should you take away from this? So one thing you should take away is that you should never use counter mode or CBC encryption by themselves without anything else. Because we saw with counter mode how you could replace bits in the message the same way we did with one-time pad. We saw with CBC mode how you could replace parts of the message and it wouldn't sort of fail decryption. So this means that you always want to have some kind of authentication involved. The other thing to take away is encrypted MAC is better than the other alternatives. Or you can use one of these dedicated modes that I just referred to that provide authentication and encryption at the same time. So this is sort of, encryption hygiene is the way to think about this. Okay, so that was enough about block ciphers and about hash functions. Now, the next topic I want to talk about is what do we do if we want to have a password, we want to encrypt things with a password. So one way this is used, it turns out when you log into one of our department workstations, you type your password when you log in. Your machine sends a message to our network server. The network server sends back a message that's been encrypted with your password. And the way you verify your password is, can you decrypt that message? So you are not actually sending your password to a server when you log in. It's the server sending you something encrypted, and if you can decrypt it and find what the contents inside, that's how you prove how you are. Only someone who knows the password can decrypt it. This means that we need to be able to take a password and encrypt something with it. Now, password is just a very random length string, but for encryption, we actually need a key of a particular length. And so the question is, if we have the scenario, what do we do to make this look good? Yes?
You allow maximum size.
What?
You allow maximum size for the password.
You don't have to. I mean, there are people out there who will have like 34 or 50 character passwords, and either, mostly they will be saved some other location and then automatically pasted in. So passwords could really be any length is what we would like here, or no requirements. I mean, we would certainly like to avoid short passwords because short passwords, you can just try everything. So that is actually a good point, is to think about what do we want from this. So how is using a password different than using a randomly generated key? You have a message, comment?
I was going to say we can use a hash to make the password.
Right, okay, so we can use a hash. A hash has a nice property that you pass in some input and it produces, a fixed size output. And that fixed size output can be truncated, or, you can hash it multiple times to make it longer if you need. So that is the building block we will use to make an encryption key. Okay, so we've solved one problem of taking a variable length key and making a password from it. What are the other things we need to do for this to be a good mechanism? So what is the problem of encrypting things with a password? Yes?
Typically, the user has to remember it.
Okay, so user has to remember passwords. So that means the next step is passwords are short. They are likely things like dates, phone numbers that have well-known formats, or they're words in a language, or words with simple substitutions. Yes?
Yes.
Right, so, and that goes to words passwords can be guessed. So this means that what the attack we're worried about is sort of a dictionary attack of some sort, where somebody has pre-computed a list of possible passwords, and they want to see, do any of these passwords match up here? Now this is not the same, does any of the passwords use the actual key? This is not the same as the attack where you actually are given a list of hash passwords. Here you see a message encrypted with a password. You are not given a database of passwords that you're then trying to break. So it's a slightly different scenario than that. So you cannot sort of pre-compute what the encrypted data should look like because you don't know what the message will be. So what is the security concern we're trying to solve here? So we know that passwords are guessable. We're going to encrypt things. What are the kinds of techniques we want to use here that will make it harder to reverse this? Right, so we can definitely salt the password. And how will salting the password help us?
Make it hard to guess. Like password is used encrypted.
Okay, so it makes it harder, but the salt is sent in public. So when you encrypt a message this way, you would have to send the salt along with it, because when you log in, you don't type your salt, right? Which means when you log in, the server, when it sends a message encrypted with your password, has to send the salt along also. So how does having salt in this scenario help? So, yes?
It prevents the dictionary attack.
So it prevents a dictionary attack in what way? I mean, if I can have a list, a text file that has 100,000 passwords in it in clear text, and then once I see the salt, I can apply the hash function and create 100,000 keys at that point. And so in that sense, I can't apply the hash function though before I see the salt. So it provides some steps because I don't have to do this hash function. So other thoughts on what we could do to make this slower or to make it harder? So the way you should be thinking is, I sort of gave you a hint with that last step, which is if you don't know the salt, you can't compute the hash until you actually see the message with the salt in it. What this means is that the way we can make this harder is by making it slower to compute the hash, to actually take your string, your password string, and to convert it to a hash. And think about this is okay, because when you're logging in, you're a human typing a password, and you type pretty slowly, right? So it may take you a second to type your password. So if it takes another second to actually apply the hash before you try to log in, that's not necessarily so bad. It might be a little slow. Maybe we make it a quarter of a second to compute the hash. But if you're an attacker trying 100,000 passwords, a quarter of a second kind of adds up when you're attacking 100,000 or a million passwords. And so that is kind of the goal, is how do we make it really slow to compute hashes? So we want to sort of use this HMAC function as a primitive to create keys from a password. So there's a protocol called password-based key derivation, or password-based key derivation function. And it's going to use a salt, and we can produce multiple keys out of it. And the idea is we take the password, we append the salt, we're going to append a counter, which will let us create different keys. If we need keys for different purposes, we can get different keys out of it this way. And then we can repeat this as many times as we want. We can apply the hash function lots and lots and lots of times. And so we can just apply more and more hash functions. If each one takes a millisecond, we can make this take a second by applying it 1,000 times. If it takes a microsecond, we can do it 1,000,000 times. And it's not that hard, but you can't reverse it unless you can't generate the key out of this unless you apply it this many times. So that gives us the key. So when you want to encrypt with a key, what we're going to do is we're going to take the salt, we're going to append it to, we're going to take some random input, we're going to take that random input and split it into a salt and then some random padding R prime. We're then going to apply our password-based key derivation function to the password and the salt to create a key. We can then encrypt the data using the key we generated, the message, and this extra randomness that we have. That randomness can go into padding, for example. And then we are going to return the salt and the ciphertext. So this is the basic way you encrypt something securely with a password. So we need randomness in this step when we're communicating. And note that in this case, we might actually want to use a different salt every time you use your password, so that somebody can't, having seen your salt, you log in once, doesn't get an advantage the next time, because they have to do it again the next time you log in. To decrypt, we're going to take the ciphertext C, we're going to split that into a salt and C prime, which is the remaining ciphertext. We're then going to apply password-based key derivation to the salt and the password that we know because we share the password. We can then decrypt, apply the encryption function in reverse, encrypt prime, we're going to decrypt it, that's a typo on my slide, and now we'll return the message. And so this is sort of how you do symmetric encryption with a password in a relatively secure way. Any questions on this protocol? It's not a lot of surprises here, I think.
So, regarding salt to randomness, it's a salt R prime.
So what we are saying, this is at the top where we're encrypting. So what we are doing is we are taking our randomness and we are splitting it, and we're using it for two purposes. So it's a little bit of a weird syntax, because we're saying that we're going to take the randomness, and part of it will be the salt, and the remaining part of that randomness will be R prime. Okay. So you would normally write it the other way. This is really, you can think of this as casting the randomness into a structure that has two fields in it. And the same thing is in the bottom, where we're taking the ciphertext and casting it into a structure with the salt followed by the embedded ciphertext. I see people still staring at this. Should I give you a little lot more time? So the attack on this is that there's a lot of really commonly used passwords. So what's great, actually, for security research is there's been all these leaks of millions and millions of passwords, which means that people have actually really good data on what kind of passwords people use. And so this is a study of password use, and it sort of shows of this big data set, I don't know the size, how many people had this password, right? So 1, 2, 3, 4, 5, 6 was used by 290,000 people. 1, 2, 3, 4, 5 was used by 79,000 people. Password was used by 61,000. Princess by 35,000. Rock You, 22,000. I'm not sure I would have guessed many of these, the numbers I would guess, I'm not sure the other ones I would have guessed. Baby Girl, Monkey, Jessica as being like super popular passwords. I didn't know that Jessica was such a popular name. So, what this means is that if you pick one, if you're trying to break into this, you definitely want to try passwords in popularity order, right? Because you can, even if computing that hash function takes you a second, for a decent number of passwords, for a lot of people, just trying the top 100 or 200 or 1,000 or 10,000 will get you pretty far. And again, this should scare you into thinking about how you pick passwords. Hopefully nobody in this room has a password that shows up on this list for anything that they care about. The other thing to note is sort of the length of passwords and the complexity. Again, this tells you when you're building your dictionary, what kind of words should you put in the dictionary. Right? That 41% have only lowercase letters, no numbers, no symbols. People have mixed, if you add another 40%, it's just numbers and letters, no special characters. So you can get pretty far with fairly simple passwords in a dictionary. So if we think about a brute force attack on this mechanism, one way to think about it is one kind of attack is a known plain text attack. This is where we know what the message is, we have the encrypted version, and we're trying to get the password out. And so what we can do here is sort of create a dictionary of all possible inputs. So there's a couple different ways to do this. One is to assume we have some ciphertext that we're splitting into this random salt and the embedded ciphertext. Then for every password in our dictionary, we are going to try to take the ciphertext and encrypt the known message to create a new ciphertext. And this will tell us if the ciphertexts are the same, we know the password. So we're basically taking all of our random passwords, encrypting something, see if it matches the ciphertext that we're given back, given the randomness that we have as input. So to do this, the operation we're doing here is to do this encryption every time. So that's sort of the, we also have to do this for every different piece of for different random. So here we know what the randomness is that we're going to pass into this encryption, but we have to do it for each different piece of password. So does this brute force attack make sense? Right, because we can sort of see what the salt is or the initialization vector is. So there's another way to do it, which is to take every password in the database. We can try to decrypt the message with the password, and if the message looks right, then we can say this is the password. So here we made this one. We don't actually have to know what the message is to compare because we're not encrypting things. We're just trying to decrypt everything, and we can just say, messages that are in English have a certain property, like they have words, that they're not garbage, that if it's a data structure being encrypted, we know what the fields are and the range of values is. And so here we are doing something that might be slightly easier to do because we don't have to know what the message is. So here is sort of why we think this is secure. So the idea is that we can slow down attacks by an arbitrary factor by having some number of hash functions and just making it longer and longer and slower. So this means that as computers get faster, we can take the same approach and slow it down every year if we want. As Moore's law gives us faster computers, we just make applying this hash function slower. And the salt, as we've talked before, creates different derived keys so that you can't sort of just create keys once every time. And it means that we saw before, you really can't pre-compute anything. You really have to start with the clear text password and then do all the computation after you've seen the salt. So that is why salting helps here, is all you can do is make a list of words in it, in the beginning, you can't do any other part of this attack offline. So one question is how fast is this? So the OpenSSL has a way of speeding things. So you can see for different size, for creating, for either doing encryption with AES 128 or for doing SHA-1, you can sort of see how fast it is. So we can see that on 16-bit blocks, we can do 4 million SHA-1s in 3 seconds. So they take a little bit over a microsecond per hash computation. For AES 128, we can do 2.27 million AES 128 encryption. So AES is pretty fast. So this tells you roughly how many things you want, how many different times you want to apply this, and it tells you if you're applying it a number of times, you know, roughly how long it takes you to break a password a different size. Because, you know, this means that we can test 252 passwords a second on this computer with applying the hash 4,000 times. So this tells us how long it takes. So just guessing a million numbers takes what, about an hour or so. If you have a mix of letters and numbers that are 6 characters and there's all possibilities, so they're totally random, then we get to about 100 days. So this also can help you figure out, you know, how often should you potentially change your password, so that if somebody can guess it in 100 days, then you might want to make that information not as valuable. Okay. Yes? Right? So that's for a longer password, an 8-character password that has upper lowercase letters, 10 digits, and 10 symbols. So that makes 72 symbols for 8 characters. If it's totally random, then it gives you 72 to the 8 possible different passwords to check. Yes. Right. So yeah, but this sort of tells you as a user, like how hard it is to break your password if it's a totally random 8-character password, or if it's a totally random 6-character password. Okay, so short passwords are bad. Don't use them for things that you care about securing. Having numbers and symbols in a mix of case definitely helps, especially if it's not in a predictable way. Using salting means that people can't pre-compute things. Using iteration allows you to slow things down arbitrarily, so that even if somebody can you know, break it and try possible combinations, you can make it slow and painful. So one thing to note, by the way, is that those numbers were for using a single computer. If you're running on at Amazon, for example, and you're running on 1,000 computers, you can do that 1,000 times faster. And so that means that even if it would take 1,000 days to break a password, you know, if you do it at Amazon, you could potentially do it in a day, although it would cost you a lot. Okay, any more questions on passwords? So hopefully now you know how to use them, how to make them secure, what protocols that use them should look like. Okay, so we're now going to sort of talk about asymmetric encryption. And remember, the big idea here is that we want to not have to have a shared secret between the person encrypting a message and decrypting a message. That whatever you use to encrypt the message can be totally public and known to the world, but only somebody who knows the secret can decrypt it. And the basis for this is what's called a trapdoor function. So a trapdoor function is really something that's easy to compute in one direction, but very hard to compute in the other direction unless you know where the trapdoor is. So for example, think about locking a padlock or locking a door. It's very easy to lock the door. Anybody can lock the door or padlock. You know, sometimes you just pull the door shut, it locks itself. But then opening the door without the key is very difficult. And it's the same idea. Anybody can encrypt something with a public key, but reversing that and trying to decrypt it without knowing the secret key should be very difficult. So what you need are operations that are easy to do in one direction, hard to do in another direction. And a canonical or an example that people use for encryption is large numbers. So if I give you 2 big prime numbers, you can multiply them fairly easily. You know, it's not that fast, but it's not that slow to multiply numbers. If I give you a really big prime number, however, figuring out what a really big composite number, finding the factors of that big composite number is very slow. And so we can use this to say, what if we can say encrypting is sort of like multiplying numbers and decrypting is sort of like factoring numbers in some way. And so that is sort of the basis for how RSA encryption works. So this encryption mechanism was invented in 1978 by these guys at MIT. I know Ron Rivest is still there, a pretty interesting guy. It got the Turing Award. They took this idea and created a company called RSA Data Securities to actually try to make money off of this mechanism. And they did that because they patented the idea of using this mechanism for encrypting data. So they had a patent on the only known way of doing asymmetric key encryption. And then if you wanted to use that, you had to pay them a lot of money, and they would do implementations of this that you could then, get their code to actually do encryption. And it turns out that to some extent their business was a failure, and that they charged so much money nobody wanted to use it. And so public key encryption was very rarely used for these 17 years after they published this and got a patent on it, because the company wanted so much money. And it was really only after the patent expired that everybody started using it. Because, for example, you couldn't put it in open source software. So if you wanted to have a free web browser that could do connections, they wouldn't let you do that. If you wanted to have a free web server that allowed secure connections, you couldn't do that. Everything had to be paid for. And so really it was sort of the end of that patent that let sort of the internet and secure commerce flourish by making this publicly available. So the company RSA sort of still exists and it thrives. They turned into sort of a general computer security company. I think they were bought by EMC, and they still have a big security conference every year, and they're very influential. And they do a lot of research on encryption mechanisms, but they sort of can't just like make money off of selling this patent anymore.